In part 2 of limits and continuity, the main focus is on properties of limits and also infinite limits related to vertical and horizontal asymptotes. Problem 1 says to use the graphs of f of x and g of x that you see below to estimate the following limits that are related to sums, linear combinations, products, and quotients. We also see that these are also related to left and right hand limits. We talked about that graphically last time. So start with part A. The limit as x approaches 1 from the left, again that minus sign to the right of the number means from the left. If it were a plus sign to the right of the number, it would mean from the right, of the sum f of x plus g of x. The first thing to write down is just the key property of limits that we want to use here. The limit as x approaches 1 from the left of the sum f of x plus g of x. Assuming these limits exist, and in writing this equation I'm really assuming these limits exist, is the sum of the limits of the individual functions. The limit as x approaches 1 from the left of f of x plus the limit as x approaches 1 from the left of g of x. All right, we're assuming those limits exist when we write this down. Do they exist? We can see from the graph what happens. We're approaching 1 from the left. We focus on this piece of the graph for f of x and this piece of the graph for g of x. We think about what is happening to the second coordinates, the y values, as x gets closer and closer to 1 without actually equaling 1, because you can see this function, both of these functions, are undefined at 1. That's irrelevant though. It doesn't matter. These limits still exist. The second coordinates you can see here are approaching the second coordinate of the quote-unquote missing point, which is 3. That is what this limit is right here. It's 3, even though the function never actually equals 3. And even though we're not letting x actually equal 1. That's the hardest part here. We're letting x get arbitrarily close to 1. As x gets closer and closer to 1, I can make the outputs of this function get closer and closer to 3. Arbitrarily close by making x sufficiently close to 1. All right, and what about with g of x? You can see the second coordinates here are approaching the second coordinate of the quote-unquote missing point here, 2. So this limit exists n equals 2. So the final answer is 3 plus 2 equals 5. Part B. Now we're letting x approach 1 from the right. You see the plus sign there. Now it's not f of x plus g of x. It's 3 times f of x plus 4 times g of x. That's called a linear combination. You do what you would hope to do. You would hope this is true. You essentially factor the limit symbol through the parentheses and factor out the constants as well. That's not literally what's happening. The limit symbol is not a number, so you're not doing any kind of multiplication here, but it's similar to that kind of thing. You could think of it in 2 steps. You've got 2 functions here that are being added by what we used in part A. This limit that you see here would be the same as the limit as x approaches 1 from the right of 3 times f of x plus the limit as x approaches 1 from the right of 4 times g of x. It's supposed to be a 4 times g of x. And then you can factor out those constants. Do these rules make sense? Well, I'm not proving them, we're just using them. Think about it. I'm letting x approach 1 from the right, and I'm wondering what happens to this expression as x gets closer and closer to 1 from the right. If you could figure out what f of x and g of x individually get close to, and in fact you can see what they get closer and closer to, 2 for f of x, I'm approaching 1 from the right, and 4 for g of x. This is getting closer and closer to 2, this is getting closer and closer to 4. Intuitively, it should make sense that this entire expression gets closer and closer to 3 times 2 plus 4 times 4. 6 plus 16, 22 should be the answer. I'm just being a little bit more formal in writing out the properties here. The next property being that I can factor these constants out in front and write 3 times the limit as x approaches 1 from the right of f of x and 4 times the limit as x approaches 1 from the right of g of x. And yeah, now again, look at the graph. I'm letting x approach 1 from the right. The outputs of f of x are approaching 2. They're getting as close as I like to 2. With g of x, I'm letting x approach 1 from the right. The outputs are getting closer and closer to 4. So this becomes, again, 3 times 2 plus 4 times 4. 6 plus 16 is 22. Okay, so that's the answer for part B. Part C. Let x approach 1 from the left and figure out the limit of the product f of x times g of x. We already should be able to predict the answer. I'm letting x approach 1 from the left. F of x is approaching 3, second coordinate at that point. G of x is approaching 2. If the values of f are approaching 3 and the values of g are approaching 2, it should make intuitive sense that the values of f times g are approaching 3 times 2 is 6. But now we be a bit more formal about it in using official properties of limits. Limit as x approaches 1 from the left of f of x times g of x. Assuming the limits of the individual functions exist, that's the product of the individual limits. Maybe use parentheses here for extra emphasis. This limit, if it exists as a number, this limit, if it exists as a number, and the limit of the product here is the product of those two limits. And again, coming back up here, the limit of f is 3 and the limit of g is 2 as I approach 1 from the left. So this becomes 3 times 2 equals 6. Yeah, 6 is going to be the answer there. On to part D. Now I'm letting x approach 1 from the right, back to the right, and now I have a quotient. Similar kinds of things hold. Limit as x approaches 1 from the right of f of x divided by g of x. The limit of a quotient is the quotient of the limits. Two assumptions going on here. One, you're assuming the limit exists, and secondly, you're assuming you're not dividing by 0. So in writing this, I'm making those assumptions. I really haven't proved them, but I'll go ahead and write them. The proof is what I see now when I look at the graphs, letting x approach 1 from the right. F of x approaches 2, g of x approaches 4, so this becomes 2 divided by 4, which is 1/2. Okay, you can find the answers to parts C and D without graphing the product f of x times g of x or the quotient f of x divided by g of x. Or for that matter, in A and B, we didn't make any graphs either. We were using these graphs. Problem 2 is related to limits and continuity. Find a value of the constant k so that the following function is continuous at the value x equals 1. You can see this is a piecewise function. F of x equals k times x if x is 0 is less than or equal to x is less than or equal to 1. And it equals negative x squared plus 2x plus 4 if x is greater than 1. Certainly this function is continuous everywhere possibly except 1. Well, except 1 is the only possible place where it's discontinuous. And in fact, there is only one value of k that we can choose to make this function continuous at 1. Think about what the graph of this would look like before we go ahead and find it. For x strictly greater than 1, the graph is of this quadratic. Graphs of quadratics are parabolas. Let's go ahead and use the technology that we have to go ahead and make that graph, though we will only focus on the part where x is greater than 1. So we have negative x squared plus 2x plus 4. Window will start x at 1 and we'll go to say 5 or something. It is going to be a parabola opening downward because the coefficient of x squared is negative. Let's make the x scale 1. Let y go, I don't know, from negative 5 to 5 just to see what we see here. I do see that the value of this when x is 0 is 4, but I'm focused on when x is bigger than 1. I guess I can see that the value when x is 1 is 5, so I should probably go up a bit bigger than 5 here. To 10, say, and let's just see what we see here. So the graph looks about like that. Looks like it has an intercept. This is 1 here, this is 2. A little bit bigger than 3 is where the intercept is. That's not a real big deal. This would be up at 5, and the graph is going to look something like that. Okay? All right, what about this part when x is between 0 and 1? It's k times x. If k is negative, that's a graph that goes down like that. If k is 0, it goes across like that. If k is positive, it goes up like this. Intuitively, we want to make sure that these graphs match up. All right, this is not too hard. To make those match up, I need to make the slope of that line be 5. K must be 5. That is the answer. To be a bit more official about it in terms of giving reasons related to limits, I want the limit as x approaches 1 of this function to equal the function value at 1. That's what it means to be continuous at 1. The function value at x equals 1 is given by this formula because 1 is included in this interval. So this would be k times 1, which is k. And I want that limit to be true whether I'm letting x approach 1 from the left or 1 from the right. It's definitely true when x is approaching 1 from the left because this formula, this is the piece of the formula to use when x is less than 1. What about when x is approaching 1 from the right? Then I need to think about that formula, the second formula there. If x is approaching 1 from the right, technically speaking, I need to think about the second formula, approaching 1 from the right, negative x squared plus 2x plus 4, because that's the formula that's relevant when x is greater than 1. And it doesn't matter that 1 is not included in that interval. Remember, with limits, it really doesn't matter what happens at the value that you are letting x approach, in this case 1. I still use this formula. I can still find this limit, even though this formula is not relevant when x equals 1. But, and again, this is tricky as well, to find this limit, I do plug in 1. Okay, this is the confusing part about limits. So plug in 1, I'm going to get negative 1 squared, which means do 1 squared first and then use the negative sign, plus 2 times 1 plus 4. That'll be negative 1 plus 2 plus 4, and that is 5. That's the limit of this function as x approaches 1 from the right, equals 5. That's got to be the same as k. K has to be 5. You could say therefore, 3 dots means therefore k must equal 5. But we already knew that as the answer. We knew that this is the graph. Maybe your teacher is fine with you just giving a graphical reason. Maybe your teacher wants you to give a reason based on limits. Number 3 says use algebra and properties of limits to find two limits in part A and part B here. Notice these are different kinds of limits. These are limits at infinity, you might say, as x goes to plus infinity, which means as x gets bigger and bigger to the right without bound. Okay? We're sort of implicitly assuming that these limits exist in writing these things and saying go ahead and find them. So what this means is both of these functions ultimately are going to have horizontal asymptotes. And maybe you have enough knowledge to even guess what the horizontal asymptotes are here without even doing any calculations. However, for the purpose of this problem, we want to do calculations to confirm the answer, and we want them to be moderately rigorous calculations, though kind of similar to a problem before. I am going to be implicitly assuming that limits exist and are non-zero. In the first case, well, and in fact in both cases, the first property you might be tempted to use is the fact that the limit of a quotient is the quotient of the limits. In other words, you might be tempted to say, okay, I should bring this limit sign into the top and into the bottom. There is a problem there, though. If you do so, the limit of the top and the bottom, polynomials in this case for this rational function, are both infinity. So you'd have infinity over infinity, which, well, that's what's called an indeterminate form. Now, if you happen to know something called L'Hopital's rule, which is a calculus-related thing, you can calculate this limit with L'Hopital's rule. But we're not assuming you know calculus here. So we need to calculate the limit in some other way and not write it as infinity over infinity. Because what is infinity over infinity? Technically, it's undefined. So we need to do an algebra trick here before we use the property of limits that I was hinting at. And the algebra trick to use when you've got a rational function where the degree of the top and the bottom are the same is to multiply the top and the bottom by 1 over that highest power of x. Or in fact, divide by that highest power of x on the top and the bottom. So the highest power is the same, it's x squared, and the top and the bottom, that's going to imply this limit will exist. And I'm going to multiply the top and the bottom by 1 over x squared before I use limit properties. I think I won't bother writing the plus infinity anymore. I'll just write infinity. I've got to use the distributive property in both cases and do appropriate cancellation. 4x squared times 1 over x squared, the x squareds cancel. I'm left with 4. 5 times 1 over x squared, well, is 5 over x squared. Same kind of thing in the bottom. multiply the 1 over x squared through, you'll get 5 minus 2x times 1 over x squared is going to be 2 over x. Okay, so now what happens intuitively is you will be able to use the property that the limit of the quotient is the quotient of the limits, because the top and the bottom limits now will exist, and the bottom one will not be 0. So I will go ahead and do that. Again, this is technically not as rigorous as it could be, because in even writing these equations, I'm implicitly assuming these limits exist, and I'm also implicitly assuming the bottom limit is non-zero. That is certainly true, but it makes what I'm doing not completely rigorous in writing this. So the limit of a quotient is the quotient of the limits, assuming these limits exist and are non-zero. Now in each case you have a limit of a sum there and a limit of a difference. You can bring the limit sign through to write the limit as x approaches infinity of 4 plus the limit as x approaches infinity of 5 over x squared, all divided by the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x. We can be a little extra picky about things and say, well, like in these two expressions, I should factor out the 5 and I should factor out the 2. Maybe your teacher wants you to do that. Maybe your teacher doesn't care. Just to make the expressions you're ultimately taking the limit of a little simpler looking. Constants, by the way, I got rid of the limit sign here and here, are constant. They don't change as x changes. The limit of x of 4 as x goes to infinity is definitely 4. The graph of 4 is a horizontal line, and the limit as x goes to infinity of 5, 5 being a horizontal line at y equals 5, is also 5. I can get rid of those limit signs. And what I'm left with are a couple limits here that you look at and you say, well, shouldn't those be 0? And the answer is yes, they are 0. Now you could argue it's pretty obvious these two are both 0 as well, and so you don't really need to factor out the 5 and the 2. Again, maybe your teacher cares about that kind of thing. Maybe your teacher does not. I'm going ahead and, at least in part A, being a little extra picky about writing all those steps. Technically speaking, you could also argue that these limits being 0 need proof. We're not proving them. It should make intuitive sense as x goes to infinity, as x gets bigger and bigger without bound. 1 over x squared and 1 over x both approaches 0. They get as close to 0 as you like. But, okay, we won't go overboard there. The final answer is 4/5, 0.8. So that means this graph would have a horizontal asymptote at 4/5, y equals 4/5, as x goes to plus infinity. It's actually true as x goes to minus infinity as well. All these calculations would be valid even if I were letting x go to minus infinity. So with this function, at least, that has a horizontal asymptote at 4/5, whether x goes to plus infinity or minus infinity. However, there are some functions that can have two different horizontal asymptotes, one of which is the inverse tangent function. It's not a similar kind of function. It's the inverse tangent function. It's got two distinct horizontal asymptotes. That can happen. All right. What about part B? Part B is fairly similar. In fact, all I did was replace the x squareds with e to the x in looking at part B here. And that's going to mean similar calculations will be helpful. Similar, not exactly the same. It's not technically a rational function anymore, even though it is a ratio, because with rational functions, technically the top and the bottom must be polynomials, and if you've got an e to the x in there, it's not. The steps are pretty similar though, and what you want to end up doing here is now multiplying the top and the bottom by 1 over e to the x, or if you prefer, e to the negative x. By the way, I forgot to mention, it's not changing the fraction by doing this first algebra step, because you're really multiplying by a disguised form of 1. So it is valid. I forgot to mention that before. And then, okay, so we're doing this, use the distributive property again. E to the x times e to the negative x is 1. They cancel. So you're left with a 4. We're left with a plus 5 e to the negative x. And on the bottom, you've got e to the x times e to the negative x is 1 again. So you get a 5 minus 2x e to the negative x. Now go ahead and use the property that the limit of a quotient is the quotient of the limits, like this. Again, this is not fully rigorous because I'm implicitly assuming that these limits exist as numbers and they're not equal to infinity, and the bottom one is not 0. And I'll skip a couple steps here. Ultimately, you're going to get to the limit as x goes to infinity of 4 plus 5 times the limit as x goes to infinity of e to the negative x divided by the limit as x goes to infinity of 5 minus 2 times the limit as x goes to infinity of x times e to the negative x. I can factor out constants, but I can't factor out that x because I'm letting x change, so you can't factor something out that's not a constant here. These limits, what are they? Well, now we're also using knowledge about the behavior of e to the negative x, for example. It's exponential decay. It's got a horizontal asymptote that is the x-axis. This does go to 0. This limit equals 0. What about this limit? Again, technically, if you want to be extra careful about it, you'd want to use something called L'Hopital's rule, but that's a calculus-related thing. You could also think of it in terms of dominance. This function here is the same as x over e to the x. E to the x and x both get large as x gets large, but e to the x grows much more rapidly. It dominates x, so much so that it makes this fraction go to 0. It's not a proof, but this limit is indeed 0. And so in the end, we get the exact same answer as before. 4 plus 5 times 0 over 5 minus 2 times 0 ultimately is 4/5, the same answer as before, okay, with part A. All right, so it's a bit tricky, a bit painful, you might say, but this is a semi-rigorous way to do it. Number 4 says, does the following limit exist? This limit right here that you see? If so, find it and explain. If not, explain why not. Probably the best thing to do with such a complicated looking function, such a weird function, is maybe to graph it first and just see what you see. So let's go ahead and do that with our technology. Go to our y equals screen, clear that one out. Use parentheses. There is a way to simplify this, but I'm not going to do that yet. Sine of x plus 2x all over x. Be careful. What kind of window should we choose? So sine oscillates with period 2 pi here. So I could choose, for example, I don't know, like negative 4 pi to positive 4 pi and just see what we see here. Let's go ahead and try that. Negative 4 pi to positive 4 pi. Of course, we're only letting x go to plus infinity, but it might be good to see what happens as x goes to minus infinity as well. And maybe the same kind of thing happens. Okay, it's negative 4 pi to 4 pi. Sine of x is oscillating between negative 1 and 1. 2x is getting large either positively or negatively as x goes to plus or minus infinity, and same on the bottom there. It's hard to say what kind of y range to pick. Let's just try negative 5 to 5 and we'll see what we see here. Oops, let's see, one window range. I must have done something wrong there. Window, negative 5 to 5. Oops, I need a positive 4 pi there. 4 pi, there we go, that should do it. What do we see? Okay, we see a graph that's kind of oscillating in a weird looking way. Does seem, the oscillation, the amplitude you might call it, is kind of big when x is close to 0 and then gets smaller perhaps as x goes further from 0. Let's try changing the window. Let's go negative 6 pi to positive 6 pi. And let's focus in on where the main part of the graph is. Maybe we try 1 to 3 or so. Oh, 1 to 3 maybe? Let's change that to 3. Let's just see what we see there. We do see some oscillations that are a little bit more explicit. That's kind of nice. Pretty function. Isn't that pretty? So it's definitely oscillating all the time. I guess, yes, because of the sine function. But the oscillations, as you get further from 0, are getting smaller and smaller. Let's go back to the window and Let's just try negative 50 to 50. There are small oscillations there. But they're definitely getting smaller and smaller. Does this have a horizontal asymptote? Does it have a limit in spite of the oscillations? It looks like that's a 2 there. Looks like maybe at 2. Draw that horizontal line. It's approaching that line, it seems, as x goes to plus or minus infinity. But wait a minute. Can graphs cross their horizontal asymptotes? Is that allowed? Can I call that a horizontal asymptote? The answer is yes, you can. Graphs can cross horizontal asymptotes. It's just with rational functions, they often don't. So we're sort of used to graphs not crossing horizontal asymptotes, but this is a case where it does. So as far as giving it looks like the limit here does exist and does equal 2. One way to explain it, again, depending on what your teacher's after, is to just explain it graphically. The graph looks like this, where this is 2. It looks like this kind of thing. It's oscillating above and below that line infinitely often as x goes to plus or minus infinity, and the oscillations are getting smaller and smaller in amplitude. The function outputs are getting as close as I like to 2 by letting x be either sufficiently big in the positive direction or sufficiently big in the negative direction. So I verbally explained that and I drew a graph, so maybe that kind of thing is good enough for your teacher. Here's another thing you could do to be a little bit more rigorous, you might say. Take the function here itself and rewrite it. You can, in a sense, simplify this because you can separate this into 2 pieces, 2 separate fractions, like this. And 2x over x simplifies to 2, at least when x is non-zero. When x is 0, they're not equal, which does also tell me, technically speaking, this graph has a hole in it when x equals 0, but you don't see that in the calculator. But as we're letting x go to infinity, plus infinity or minus infinity, that's irrelevant. It doesn't matter that it's undefined when x equals 0. This part, sine of x over x, you've got a numerator that's oscillating between negative 1 and 1, and a denominator that's getting really big, either positively or negatively. Something that stays between negative 1 and 1 divided by something that's getting big is going to 0. This is going to 0 as x goes to infinity. Now, to be more official about proving that, you could use something called the squeeze theorem. Maybe I'll let you look that up. Look up a video about the squeeze theorem and its application of the squeeze theorem. It could be used to prove more rigorously that this goes to 0, but it's pretty intuitive that this is stuck between negative 1 and 1 and this is getting big. The whole entire fraction definitely can be made as close to 0 as you like. Meaning, ultimately, the entire thing goes to 0 plus 2, which is 2, as x goes to infinity. So there's a little bit more rigorous, not fully rigorous, but a little bit more rigorous explanation. And again, maybe that's good enough for your teacher. If your teacher wants you to use the squeeze theorem, you should look that up. Number 5 says to sketch the graph of a function f with all the following properties. And there are 8 properties. Yikes, looks kind of scary. Take a breath, take a step by step. Don't rush this kind of problem. Be careful with it. There are lots of places where you could make a mistake. Let's draw the graph nice and big here. Start with the fact that f of 0 is assumed to be 2. Just draw one point. Don't make any other assumptions about the graph. F of 0 is 2. Let's pretend, let's say 1 is here and 2 is there. F of 0 is 2. Plot that one point. Don't try to draw a line through that point in any direction or even a curve, because it might be wrong based on other properties that we have here in this problem. F of 5 equals 2. 1, 2, 3, 4, 5. This point is on the graph as well. Just draw the one point. There's 5. The limit as x goes to minus infinity of f of x equals 2 is the next property. Letting x get big in the negative direction, the function outputs approach 2. The horizontal line at y equals 2 is a horizontal asymptote for this function as x goes to minus infinity. Should I start drawing f? Should I draw this or maybe like that? No, we don't quite know what to draw there yet based on this. We need the other information to make sure we're not messing things up. Of course, actually, you probably are going to have freedom in this problem because there's nothing about the function being continuous on certain intervals here. So it probably wouldn't matter in the end, but let's just be careful. Next, part 4 here. The limit as x goes to 0 of f of x is 0. It was good that we didn't draw anything there besides the 1 point, because as x approaches 0 from the right or from the left, this is a two-sided limit. There's no plus or minus to the right of the 0 there. The function outputs have to approach 0. So the point 0, 0 is not on the graph, but the function approaches that point as x approaches 0. Should I draw something like this and this, or this and this? That's not so clear yet, okay? Be patient here. Limit as x approaches 2 positively or negatively, or from the left or from the right, is infinity. The vertical line at x equals 2 is going to be a vertical asymptote, is what that means. I'm letting x approach 2 from the left or the right. The function outputs get arbitrarily large. Okay, now we can start to draw a little bit more. We can draw those two pieces like that. The function outputs are approaching infinity. They're getting arbitrarily large above any horizontal line by taking x sufficiently close to 2. So let's just keep it to that much so far. Continuing here, we're almost done, just 3 more properties. The limit as x approaches 5 from the left of f of x is 2. We know f of 5 is already 2. If we let x approach 5 from the left, minus sign there means from the left, doesn't mean negative, we've got to approach the function value there. Hey, this is left continuous at 5 perhaps, or we can certainly draw it that way. All right. The limit as x approaches 5 from the right is negative 2, not positive 2. It's not right continuous at 5. I'm going to draw an open circle down here. It's not part of the graph, but I'm just emphasizing it's going to approach that. Okay, should I draw it like this or this? It doesn't really matter. In the end, we do want, as x goes to plus infinity, the function outputs to approach minus infinity. So it's simplest just to do say something like that and indicate the function is going down forever and ever here, no horizontal asymptote. And I guess with all these other things, we have freedom in how we do it. I mean, we're coming from infinity here, and we're approaching 0, so something like this is fine. I could go up right away like that, but it's maybe more natural to go down like this before coming back up here. It is a horizontal asymptote. I could approach it like that. I could, like in the previous problem, make it oscillate up and down with smaller and smaller oscillations. Probably simpler just to do it like this. And that will be a function that satisfies all these properties. So far in this video, we've not been super rigorous. That changes here in our last problem. We're going to use the intermediate value theorem to prove that this function, f of x equals x cubed plus x minus 1, that cubic, has a 0, in other words, a root, x-intercept, in the closed interval from 0 to 1, including the endpoints. That's interval notation there. In set builder notation, this would be the set of all real numbers x with the property that 0 is less than or equal to x is less than or equal to 1, a closed interval. All right. How in the world do you do this? Well, let's think intuitively about what's going on here first. You could use your calculator to graph this function. It's not too hard to graph by hand. You could plot some points. And what you will see is a graph that looks about like this. It's cubic, and it's got a y-intercept of -1 there. It's got a slope at x equals 0 of the coefficient of x, which is 1. That slope right there is 1. Looks like this. It turns out, if you are more careful on your calculator, that +1 on the x-axis might be about there. Okay, just estimating it. Maybe it goes up faster than I've drawn it here. I'm not sure. Let's go ahead and graph it on the calculator to see. Clear that out there. Why is it not clearing? My calculator was not clearing. There we go. X cubed plus x minus 1. Let's let x go from, say, -1 to 2. And y go from, I don't know, like -5 to 5. Okay, it looks like I drew it pretty accurately in that x-intercept, this 0 or root of the function, is a little closer to 1 than it is to 0. So this is a fairly accurate graph. So you can see it's got an x-intercept right there, okay? And for most people, that's good enough, right? There it is. It's got one. I have proved it from the graph. That's not a mathematical proof, though, okay? Mathematical proofs need rigor, because how do you know for sure that it actually does touch the x-axis? In drawing the graph, you were implicitly assuming it touched the x-axis. You see how that's circular reasoning? That's bad, technically speaking. Now, the intermediate value theorem is a pretty powerful tool to do this proof, and to make the proof fairly short. But if we wanted to avoid using the intermediate value theorem, it still could be proved, but you would have to go down to the foundations of real numbers. It's called real analysis. It's super complicated. We're satisfied in using the intermediate value theorem. But what does the intermediate value theorem say? IVT. It's worth taking the time to write it down. It says this. Assume you've got a function, f, that is continuous on some closed interval. I'm going to use a special kind of notation here. This kind of notation here means that the function has this closed interval from a to b as a domain and has the real number system, that's the real number system, set of real numbers, as what's called sometimes a codomain. Not the same as the idea of a range. Range is the set of all outputs. By saying this is the codomain, I'm saying the outputs of this function are real numbers, but this function is not necessarily onto. It doesn't necessarily, every real number is not necessarily an output of this function. So I'm going to assume this function is continuous, not just at 1 point or 2 points, but over the entire interval from a to b. The conclusion is, and let's also assume f of a and f of b are different from each other. Then there exists, okay, I'm not quite done here. Let's say it this way. Then, given any number such as 0, if f of a and f of b have different signs, call it k, between f of a and f of b, there exists a number c in the interval from a to b such that f of c equals k. Yikes, that's a mouthful. What's going on here? Think about it in our example. There's our function. There's the formula that defines our function. That is a polynomial function. It is certainly continuous everywhere. The continuity assumption definitely is met, and in particular, it's certainly continuous on this closed interval here. The a would be 0, the b would be 1. F of 0 is -1. What's f of 1? Plug in 1, you get 1 plus 1 minus 1 is positive 1. That's a point on the graph. F of a and f of b are different. We're trying to prove that this function has a 0, that it equals 0 somewhere, a root. C is that quantity there. The k is 0. 0 is a number between f of 0 and f of 1. -1 and 0. -1 and 1, excuse me. There must, by this theorem, exist a number c, somewhere between 0 and 1, such that f of c equals k, which is 0. Let's write it down. Let's write down a proof. It just feels like you're going in circles, doesn't it? Okay? let f of x equal the same function we have, x cubed plus x minus 1, and let the interval from a to b be the interval from 0 to 1. This proof should be written in sentences. This is a complete sentence. You can write symbols in your sentences, because that's just shorthand for certain words. You could describe everything in words. It's just shorthand here. Since we want to give reasons for things, since f is a polynomial function, it is continuous everywhere. On R, you could say, but you don't have to say that. It's certainly just continuous on the closed interval from 0 to 1. Note that f of 0 is -1 and f of 1 is +1. Those are different. And k equals 0, if I want to emphasize that it's a k, I don't have to use the letter k, satisfies the condition that it's between these outputs. F of 0 is less than k is less than f of 1. What do we say next? Now we use the theorem. The hypotheses of the theorem have been satisfied. We've got a function that's continuous on the interval. The function outputs at the endpoints are different. We've got a k, which is 0 in our case, that's between the given numbers. That means we can use the theorem. The conclusion will follow. There exists a number c. Therefore, 3 dots means therefore, by the IVT, the Intermediate Value Theorem, there exists a number c in the interval from 0 to 1. I'll use this notation. That means is an element of the interval from 0 to 1. There. If you don't like that notation, you don't have to use it. Such that f of c equals k, which is 0. We chose the k to be 0, okay, because of the purpose of the problem. We're after a root or 0 of the function. I could have chose some other k, but that's not the point of the problem. And that does it. That proves what we wanted to prove. That proves that this function has a 0, also called a root. You could also call it an x-intercept in this closed interval from 0 to 1. That is the end of the proof. We get all happy and we start talking Latin. QED means quod, if I remember correctly, quod erat demonstrandum, which means I've demonstrated what I wanted to do. I'm done. We're happy. We can do a smiley face as well. All right. Thanks for watching.